Imagine a quiet Tuesday evening when you tap a glass screen to purchase a seemingly ordinary item, perhaps a new coffee mug or a replacement phone charger. In that exact fraction of a second, an invisible, globe-spanning nervous system jolts awake. You might assume your order sits in a static queue, waiting for a human clerk with a clipboard to wander down a dusty aisle. Instead, your digital impulse instantly triggers a highly choreographed, high-speed ballet of metal, silicon, and mathematics occurring hundreds of miles away. This is the hidden front line of modern consumerism, where human desire meets absolute machine precision. To understand how that coffee mug reaches your doorstep by sunrise, we must step inside the modern fulfillment center, a space that has evolved from a simple storage shed into a massive, breathing computational engine. Driving this transformation is the AI revolution in warehouses, an unprecedented leap in how we manage physical goods. At the core of this leap is machine learning, a branch of artificial intelligence where computer systems improve their performance on a specific task by analyzing massive amounts of data rather than following strictly programmed rules. These algorithms process millions of variables in real time, dictating the fastest route for every single item. The genesis of this specific mechanical ballet can be traced back to the early 2000s, born from a profound realization about wasted human energy. Traditional logistics required workers to walk up to a dozen miles a day, pushing heavy carts through cavernous aisles to find specific products. A company named Kiva Systems looked at this exhausting, inefficient model and asked a radically simple question. What if, instead of the human walking to the inventory drove itself to the human? This inversion of the paradigm required a fleet of low-profile autonomous orange robots capable of sliding under massive storage pods, lifting them, and navigating a complex grid to deliver them directly to a stationary worker. Kiva utilized a decentralized control system, where central computers tracked the exact location of every robot and every pod, orchestrating their movements like an air traffic controller managing a swarm of thousands of drones. This early warehouse automation did not just save time, it fundamentally rewrote the spatial logic of the building, allowing shelves to be packed densely together since humans no longer needed aisles to walk through. The implications of this brilliant spatial hack were impossible to ignore, completely altering the trajectory of global commerce. In 2012, the e-commerce giant Amazon recognized the transformative power of this technology and acquired Kiva, eventually rebranding it as Amazon Robotics. This acquisition ignited an arms race across global logistics, forcing every major retailer and shipping company to rethink their operational foundations. The expectation of 2-day, then 1-day, and now same-day delivery was no longer a luxury, but a baseline consumer demand forged by the relentless efficiency of these robotic fleets. Managing these sprawling, high-speed automated ecosystems requires computational power far beyond simple pathfinding algorithms. Today, systems rely heavily on neural networks, which are complex computing architectures inspired by the human brain, designed to recognize patterns and make decisions based on vast arrays of sensory input. These networks allow central systems to predict traffic jams on the warehouse floor, dynamically reroute robots around a spilled pallet, and continuously optimize the flow of thousands of simultaneous orders. The machines are not just following lines on the floor, they are actively interpreting and reacting to a constantly shifting physical environment. Yet amidst this whirring symphony of automated efficiency, the human element remains absolutely critical, forming a fascinating and sometimes fraught binary bridge. At the edge of the robotic grid stand human workers known as pickers and stowers, who act as the final, incredibly dexterous link in the chain. The robot delivers the towering pod of assorted goods, and a screen illuminates, telling the human exactly which item to grab. The algorithm dictates the pace, the sequence, and the target, while the human provides the irreplaceable fine motor skills and visual adaptability required to identify a glass jar nestled next to a plush toy. But what happens when the sheer volume of global trade pushes this human-machine interface to its absolute physical limits? The relentless optimization of the supply chain creates an environment where every second is measured, analyzed, and squeezed for maximum output. The very algorithms designed to eliminate wasted movement also inadvertently eliminate the natural micro-breaks that humans naturally take while walking between aisles. The digital pioneers had set a course for ultimate efficiency, but they also birthed a high-pressure ecosystem where human physiology must constantly negotiate with algorithmic velocity. This tension has sparked intense public debate and forced a re-evaluation of how we design workspaces for the future. Labor advocates and occupational health researchers have begun closely studying the physical and psychological impacts of working alongside systems that never tire and never slow down. The societal impact extends far beyond the warehouse walls, challenging our legal frameworks and ethical standards regarding worker surveillance, performance metrics, and the baseline rights of individuals embedded within a giant, automated machine. To alleviate these bottlenecks and push the frontier even further, engineers are fiercely tackling the holy grail of robotics: automated picking. The challenge is immense, requiring machines to match the incredible versatility of the human hand and eye. Researchers at institutions like the MIT Center for Transportation and Logistics, along with countless private startups, are developing advanced robotic arms equipped with sophisticated computer vision and soft, adaptive grippers. These machines use deep reinforcement learning, practicing millions of grasps in simulated environments to figure out how to pick up a delicate polybag just as easily as a rigid cardboard box. The contrast between human intuition and machine learning in this context is striking. A human toddler instinctively knows how to adjust their grip when picking up a heavy, smooth object versus a light, squishy one. A robotic arm, however, must calculate vectors, friction coefficients, and pressure thresholds in real time, relying on an array of cameras and tactile sensors. While the machines are rapidly closing the gap, mastering the chaotic, unstructured environment of a mixed inventory bin remains one of the most complex puzzles in modern engineering. The real challenge lies in the unpredictable nature of the physical world, where a slightly torn barcode or a strangely shaped package can confound the most advanced vision system. When the robotic arm encounters an anomaly it cannot resolve, it must pause and signal for human intervention. This creates a new type of workflow where humans act as exception handlers, a cognitive safety net for the artificial intelligence. The human is no longer just a physical laborer but an essential problem solver bridging the gap between digital expectation and physical reality. As these technologies mature, they are quietly redrawing the maps of our urban and rural landscapes. Massive fulfillment centers, some sprawling over millions of square feet, are being constructed specifically to house these intricate automated systems, rather than to accommodate human comfort. These megastructures require massive power grids, advanced data infrastructure, and proximity to major highways, fundamentally altering local economies and traffic patterns. The invisible algorithms are now dictating the physical architecture of our world, pouring concrete and laying asphalt to serve the needs of the supply chain. Beyond the walls of the fulfillment center, AI optimization is weaving its way through every node of global logistics. Predictive analytics are now deployed to forecast consumer demand with eerie accuracy, analyzing historical purchasing data, weather patterns, and even social media trends. These systems can anticipate that a specific neighborhood in Chicago will experience a sudden spike in demand for snow shovels and hot chocolate next Tuesday, prompting the network to preemptively shift inventory across the country before a single customer even realizes they need those items. This level of predictive foresight profoundly alters the role of the human supply chain manager. Instead of reacting to sudden shortages or frantically calling suppliers, human operators now sit at the helm of massive dashboards, monitoring the health of an autonomous, self-correcting network. They set the strategic parameters, define the acceptable risk thresholds, and let the artificial intelligence handle the millions of micro-decisions required to keep the global flow of goods moving smoothly. It is a partnership where human strategic vision guides machine tactical execution. And this is just the beginning of a much deeper integration, pointing toward the tantalizing yet controversial concept of the lights-out facility. In a fully automated lights-out warehouse, the need for human presence on the active floor is entirely eliminated, allowing the facility to operate in complete darkness, without climate control, 24 hours a day. While this remains a theoretical ideal for most operations, certain highly specialized cold storage and hazardous material facilities are already approaching this level of total machine autonomy, hinting at a future where vast swaths of our infrastructure operate completely independently of human biology. The prospect of such profound automation forces us to confront difficult questions about the future of human labor and economic stability. If the machines can store, pick, pack, and eventually deliver goods with zero human intervention, what happens to the millions of people who currently rely on these jobs for their livelihood? Economists and sociologists are locked in a fierce debate, weighing the undeniable benefits of cheaper, faster goods against the potential for massive workforce displacement and the deepening of economic inequality. Yet history offers a nuanced perspective on this technological anxiety. Every major industrial revolution from the loom to the assembly line has sparked fears of widespread human obsolescence. In each instance, technology did indeed destroy specific categories of manual labor, but it also invariably created entirely new industries, professions, and economic paradigms that were previously unimaginable. The transition is always painful and disruptive, but the long-term trajectory has historically trended toward increased overall human prosperity and the elevation of labor away from dangerous, repetitive tasks. We are already witnessing the emergence of these new roles within the modern automated warehouse. A new class of worker is rising: the robot wrangler, the automation technician, the systems analyst. These individuals walk the floor not to move boxes, but to maintain the physical health of the swarm, clearing jammed tracks, recalibrating sensors, and ensuring the software is communicating flawlessly with the mechanical hardware. They are the mechanics of the new age, wielding laptops and diagnostic tools instead of wrenches and clipboards. The complexity of this maintenance is escalating as facilities begin to deploy heterogeneous fleets of robots from dozens of different manufacturers. You might have autonomous forklifts unloading trucks, mobile drive units moving storage pods, and robotic arms packing boxes, all requiring seamless interoperability. Developing the universal software protocols that allow these diverse machines to communicate, share spatial awareness, and collaborate without colliding is currently one of the most critical frontiers in robotics engineering. Industry leaders and standards organizations are working feverishly to establish these common languages, recognizing that the true power of automation lies not in isolated machines, but in interconnected cooperative systems. When a robotic forklift can instantly alert a fleet of mobile carriers about an incoming shipment, the entire facility operates as a single, cohesive organism. This level of synchronization is what ultimately allows global logistics networks to absorb massive shocks, like sudden spikes in holiday demand or unexpected disruptions in international shipping routes, with remarkable resilience. The ripple effects of this resilience touch every aspect of our modern lives, ensuring that grocery store shelves remain stocked, vital medical supplies reach hospitals on time, and the engine of global commerce continues to hum without interruption. The invisible efficiency of the automated warehouse acts as a shock absorber for society, buffering us from the chaotic realities of manufacturing delays, weather catastrophes, and fluctuating consumer panic. We have built a world that depends entirely on this uninterrupted flow, a world completely reliant on the silent, tireless labor of machines. When we compare the dusty, chaotic warehouses of the late 20th century to the pristine, algorithmic cathedrals of today, the sheer scale of human achievement becomes breathtaking. We have successfully externalized our desire for speed and convenience, encoding it into silicon and steel. We have built environments that are too complex, too fast, and too precise for the human mind to manage alone, necessitating the creation of artificial intelligences to serve as our proxies in the physical world. Yet, as we stand on the precipice of this fully automated future, we must remain acutely aware of the invisible tethers that bind us to these systems. The algorithms we design to optimize supply chains inevitably end up optimizing our own behaviors, shaping our expectations of instant gratification and subtly altering how we value time, labor, and material goods. The binary bridge we have constructed is not a one-way street. As we mold the machines to serve our needs, the machines in turn subtly mold the architecture of our society. Ultimately, the AI revolution in global logistics is a testament to the enduring, intertwined destiny of human ingenuity and artificial intelligence. From the early groundbreaking concepts of Kiva systems to the sprawling, predictive networks of tomorrow, we are witnessing the construction of a planetary-scale mechanism designed to fulfill human desire at the speed of thought. As these automated ecosystems grow more sophisticated, more autonomous, and more deeply embedded in the fabric of our daily lives, the challenge will no longer be how to build a better robot, but how to ensure that the relentless pursuit of machine efficiency always serves to elevate the human experience.